Hello everyone, today I'll be talking about diabetes and health risk prediction using machine learning. So a problem that we have in our society is that chronic illnesses such as diabetes risk often develop quietly without early symptoms, and this matters because late detection leads to severe medical complications and higher care costs. The solution is that machine learning can automate risk screening by analyzing patient health recordings to identify high-risk individuals early, allowing doctors to intervene proactively. So this is a summary of our data set and import features. We had over 1,000 patients in our original data set. Demographics and vitals include age, sex, resting blood pressure, serum cholesterol, fasting blood sugar. You can see several diagnostic indicators as well, and we had a target label of low risk or healthy and high risk with the condition present. This is our data processing workflow. We first removed the duplicates using isnol and drop duplicates. We use feature scaling, standard scaler to place all numerical features on the same scale so that large numbers such as features like cholesterol, which are measured in hundreds, don't overpower smaller numbers like blood sugar. And this is important for model training. It's much faster and more stable. Then we used train test split to train the set of 80% used as study material and 20% used as an unbiased final exam to test real-world accuracy. So you can see here, we did that, data filtering and cleaning, separated the features and targets, feature import, or feature scaling, and then train test split. You can see the training samples and testing samples there. Next, we can review the model selection, building, and training. So these are some important libraries that we needed in order to do some of the things from the previous slide, and as well as creating our model. So we used a machine learning model using artificial networks built using Keras TensorFlow. We use neural networks and machine learning because health indicators interact in complex nonlinear ways, and deep learning layers with ReLU learn these nonlinear relationships effectively. So this is how we built the model. We used a hidden layer with 16 neurons using ReLU activation. Second hidden layer using 8 neurons, again with ReLU activation, and an output layer using sigmoid activation, and that outputs a probability score between 0 and 1 for risk or not at high risk. Then we trained the model, we compiled using Atom Optimizer and binary cross entropy, and we trained over 100 cycles in batches of 16. So this is the confusion matrix and the results of the performance results and evaluation. So you can see here that there are 25 true negatives based on the 61 test patients, 22 true positives, so high-risk patients correctly identified, 7 false positives, so healthy mistakenly flagged as high risk, and 7 false negatives, high-risk patients mistakenly labeled as low risk. Here you can see the overall accuracy, sensitivity, specificity, and precision. Here's just a more organized data table representing that information. So for precision here, you can see that 76, when the model flags someone as high risk, it's correct 76% of the time. A recall of 76 means the model successfully catches 76% of all actual high-risk cases. An F1 score of 76 is the balanced harmonic mean combining precision and recall. So there's high performance consistency across both healthy and high-risk patient groups, and the macro and weighted averages sitting around 0.77 prove that the model performs consistently across both classes without bias. So clinically, recall matters most in healthcare, so minimizing false negatives to avoid missing sick patients. And model evaluation, 77% test accuracy proves pretty good generalizability to unseen patient data without severe overfitting, but future work could include collecting more patient data to improve the statistical confidence, as an example. And thank you for listening, and have a good day.